Hi everyone, my name is Sagie Gadasi. I'm a PhD student in the laser group of Nir Davidson and Asher Frizem in the Weizmann Institute of Science in Israel. And today I will tell you about our work on laser networks as optimization machines. This work was done together with Igor Gershenzon and Geva Arwas. So optimization problems are very common in both science and industry, from face recognition, through route planning in the traveling salesman problem, the way protein fold in the drug discovery field, and even the problem of finding the ground state of the classical 2D Ising model. Most of these problems are proven to belong to the NP hard class, to the non-deterministic polynomial time class, and that means that if we use brute force algorithms on standard computers, the computation time scales exponentially with the problem size. An interesting property of NP hard problem is that they can be mapped from one to another relatively easily. And that means that in principle, it is enough to solve one of these problems, like the 2D Ising problem, in order to solve most of the other problems in the class. To solve these problems efficiently, algorithms that are inspired by physical systems were developed. So with this algorithm, the optimization problem is converted into a ground state search problem. The algorithm maps the optimization function to the energy landscape of the physical system and then mimics the physical mechanism that takes the system to the low energy states. So the algorithm can mimic the stochastic dynamics of cooling metal or simulate the relaxation of quantum system to the ground state. An alternative is to use specialized physical systems instead and let them find the ground state. They may be able to do it more efficiently. One type of such a system is the gain-dissipative optical oscillators network. With this system, we aim to find the ground state of the classical spin model. So in the case of network of laser, the laser phase, which can take any value between 0 and 2 pi, is mapped to the direction of an XY spin. In the case of network of the generate optical parametric oscillator of DOPOs, the DOPO phase, which takes only binary values of either 0 or pi, is mapped to the direction of an Ising spin. Now, it's important to note that in order for the mapping to be correct, we need that all the other degrees of freedom of these oscillators, except for the phase, like the amplitude, polarization, wavelength, these degrees of freedoms must be frozen. The oscillators themselves are coupled by dissipative coupling, and that means that the loss of the network depends on the relative phase between the oscillators. So in order to simulate a spin system, we need to couple the oscillators in the same way that the spins are coupled. So let's consider the correspondence between the optimization problem and the physical system. So here, the optimization function is the energy landscape of the XY spin system, which is a function of the spin's directions, and it is mapped to the loss landscape of the laser network, which is a function of the relative phases between the oscillators. We want to find the ground state of the spin system by letting the laser network find the minimal loss state. Now notice that correspondence is not enough because each of these minima points corresponds to a stable lasing fixed point. So in order to ensure evolution to the ground state, the following scheme was suggested by the group of Yamamoto back at 2014. So we start by pumping the system well below the threshold, and then we increase the pump slowly. And when the pump crosses the threshold, the system starts to laze with the only available state, which is the minimal loss state. Now, since this is a stable fixed point, increasing the pump further won't change the lasing state. So in this work, we show that in a general network of identical lasers, the amplitudes are inherently not uniform. And therefore, the mapping of the laser state to the XY spin minimum breaks, and it breaks most severely near the threshold. But don't worry, we also suggest a solution. So to investigate the problem of amplitude heterogeneity on the mapping of the laser state to the XY minimum, we consider a simple laser network that acts as an XY machine and let it solve the house graph. So this is the house graph, 5 spins that are connected to their nearest neighbors with a negative coupling. And the Hamiltonian that describes the system is the following Hamiltonian, where kappa is the coupling coefficient and phi n is the angle of the nth spin. Now, since we have only nearest neighbor coupling and the coupling is negative and constant, we can rewrite the Hamiltonian in the following way. And now it is clear that in order to minimize the energy, the spins will prefer to arrange with in opposite directions. So for example, if we had only 4 spins on this square, the ground state will be the out of phase configuration when each 2 spins arrange in exactly in the opposite direction. But since we had this 5th spin, the spins have to compromise. And so this is the ground state of the house graph with negative coupling. When we let the laser network to simulate this house graph, we find that the minimal loss state is the following state. The four lasers on the square arranged in a 0 pi configuration, and the fifth laser completely turned off. Now, while in the XY spin system, the spins had to compromise, the laser network uses its amplitude degree of freedom to find a state with even lower loss than this state. Now, of course, in this situation, the mapping breaks. It's not the same problem. Now, I remind you that the minimal loss state is the state that the laser network finds when it just crosses the threshold. So when we look back on the idea of finding the ground state by crossing the threshold, we understand that there is an inherent contradiction between finding the ground state near the threshold and accurately map the laser state to the XY minimum. So again, the source for this contradiction is that while in the XY system, each spin has only 1 degree of freedom, which is the angle, in the laser network, each element has 2 degrees of freedom, the phase and the amplitude. So in order to restore the mapping, we suggest to force the lasers to have the same amplitude, and we suggest to do it by controlling the loss rates of the individual lasers. So we also show that if we find some loss pattern, some loss vector that gives a uniform intensity, then there is an exact mapping between the laser state and an XY minimum, and also this loss vector is unique. There is no other loss vector that can map the laser network to the same XY minimum. So to demonstrate this experimentally, we use the following experimental arrangement. This is the schematic drawing of the degenerate ring cavity laser, which we turn into digital by inserting this spatial light modulator inside. Now, this SLM has more than 2 million pixels, and it works very hard for us. It allows us to draw arbitrary network geometry with thousands of lasers, and it also allows us to control the loss and the relative detuning of each of the lasers independently. So to create a network of identical lasers, we apply 2 feedback loops, one over the loss of the system and one over the relative detuning to compensate for inhomogenities and aberrations of the cavities. So although this cavity is 5 meters long and composed of many optical elements, the lasers are identical with precision better than lambda over 100. The coupling between the lasers is done by scattering light between the lasers by this aperture. So we start the experiment in the following way. We first create a network of identical lasers on the house graph, and you can see that the 4 lasers on the square have the same amplitude, while the 5th laser is much, much weaker. So when we have identical lasers, we have non-uniform amplitudes, and then we apply a loss feedback loop or amplitude feedback loop in order to find a state with equal amplitudes. So after applying this feedback loop, we get this mode with much more uniform amplitudes. But again, note that in this case, the lasers are not identical anymore because each laser has different loss. So in order to demonstrate the importance of the loss vector, and more specifically, the amplitude uniformity on the correct mapping of the laser network to the XY minimum, we perform the following experiment. So here I show the intensity heterogeneity of the lasers as a function of X, where X scans the added loss pattern, where when X equals 0, the lasers are identical, no loss pattern is added. And when X equals 1, the lasers have the same amplitude. Here I show the deviation of the phase of between these 2 lasers from the XY minimum as a function of this parameter X. So when X equals 0, the lasers are identical and the amplitudes are not uniform. And you can see that there is a large deviation of the phase from the XY minimum. As we scan X and get to the point where the amplitudes are uniform, the mapping between the laser state and the XY minimum is exact. So we repeated this experiment with different pump values and different coupling strength. And we can see here in black, where the pump is way above the threshold, the intensities are less sensitive to the loss vector. And also the deviation from the XY is less dramatic. But again, now the pump is way above the threshold. As the pump is getting closer to the threshold, as is seen here by these blue and green curves, then the amplitude become much more dependent on the correct loss vector, and the mapping becomes exact only near the point where the loss vector is the exact loss vector that gives uniform intensities. So these results demonstrate the importance of the loss vector and the amplitude uniformity on the mapping to the XY spin system. Here I show the results from previous slides on a single graph, where here is the deviation from the XY minimum, and here is the amplitude heterogeneity or intensity heterogeneity. And you can see that there is a data collapse of all the data from the different experiment, which shows that the deviation of the phase depends only on the amplitude uniformity. So in this work, we demonstrated the use of a laser network as an optimization machine, and we discussed the problem of amplitude heterogeneity, and we showed that as the system gets closer and closer to the threshold, the amplitude heterogeneity increases, and therefore the mapping to the each spin system breaks. We also suggested a scheme for to solve this amplitude heterogeneity problem by controlling the loss rate of each of the lasers independently, and by that restoring the accurate mapping of the laser state to the XY spin system. Questions?